Good morning. Let us start a very interesting subject, linear momentum equations, which we used for river flow simulations. Today I will derive it for linear momentum equations for three-dimensional forms, which is the Navier-Stokes equations, as well as also we are derived for linear momentum equations for river flow. So, try to compare two equations and the complicities what is there. I am not going to derive the step by steps. I do encourage all of you follow any of the fluid mechanics books for getting the step by step derivations of the Saint-Binet equations or Navier-Stokes equations. But here I will highlight you the major assumptions, major concept what we follow to derive Navier-Stokes equations as well as Saint-Binet equations for the river flow. Try to give you the examples and simulations files. Before that, I just want to talking about reference book that mostly we are following on the fluid hydrodynamics books for these presentations, but you can look at the similar type of derivations are available in any others hydraulics book. Let us go for the Euler equations. That is what I want to summarize you. Last class we discussed that when you consider a infinitely small control volumes which is having the dimension of dx, dy, dz, and if you consider the pressures and the velocity, both the fields continuous functions in these infinite small domains control volume, what could be the mass conservation equations? Again we are looking at what could be the linear momentum equations for in-viscous flow. That is what we have derived. For in-viscous flow, there is no frictions components, there is no viscous stress components. Because of that, only you will have the pressure field variations in the fluid control volumes. So, we have only a pressure variations, there is no frictional part, no viscous effects, no shear stress components. So, only we have the pressure variations, and considering these control volumes and we try to find out what will be the pressure variations if I am considering these control volumes in a dx by 2 distance backward and the forwards, what could be the pressure if at the center point plane the pressure is P. That is what using a Taylor series expansions of first two terms we can define the pressure variations and multiplied with area we get the force. Pressure into area is a force. So, we know what is a force acting on this plane, similarly what is a force acting in the back plane of these infinitely small control volumes of dx, dy, dz. Using Newton's second laws of the motions, the sum of the force is acting is equal to the mass into accelerations, which is we know it. So, the same things we have applied for these control volumes as it has the pressure variabilities and the velocity variations. That is considering that control volumes we got these derivations. If you look at it is very simple derivations, the pressure force and equating with a gravity force components, that what is equal to the mass into accelerations. That the accelerations component, it has a local accelerations and the convective accelerations. More detail about the local accelerations and convective accelerations you can follow any fluid mechanics books. Fluid kinematics you can follow it, you can try to understand it, how interesting to know it, what is a local accelerations, what is a convective accelerations. That is what is equal to the force due to the pressure imbalance. That is what per unit mass, that is the reasons we have this part. Then you have a gravity force components. Since it is a three dimensionally, three coordinate directions, we can write this the same Newton's second laws. So, we can have a three linear momentum equations, only it's a difference between these, that first one for the x directions, and then we have y directions and you have a z directions, and if you look at this u, v, w, those are things are changing it, and the pressure gradient in this is the x direction, this is the y direction, this is z direction, acceleration component at the x direction, y and z direction. A simple force into mass into accelerations, that is what is we have applied it. Force is equal to mass into accelerations at a smaller infinite small control volumes, where we consider the pressures fields have the continuous functions, the velocity has a continuous functions in terms of the x, y, z and the t, the space coordinates and the time coordinates. So, time directions. So, considering that, we can develop these equations, and this equation is known as Euler equations. Okay. But try to look at these equations. These are nonlinear partial differential equations. This is a nonlinear partial differential equations in terms of u, v, w and the phi. So, 4 unknowns we have. So, we need to need another equations, which is the continuity equations is available to us in a 3-dimensional form. So, with these 3 equations plus the continuity equations, the set of the equations, if you can solve it, today's world it is possible using the numerical solutions. If we solve it, we can get it u, v, w and the p variations, any of the fluid flow problems. That is with a assumption is inviscid flow, the flow regions where the viscosity does not dominate much, or the significance of the viscous stresses are very less, which can be neglected for a fluid domains. We can apply this Euler equation solvers with having these 3 linear momentum equations and the continuity equations. That is what we do it, the solutions of the Euler equations, but it is a nonlinear partial differential equations with having 4 dependent variables u, v, w and p and 4 independent variable x, y, z, that is the space coordinates, and the t is the time dimensions. That is what we do it, and nowadays it is easy to solve these Euler equations with the continuity equations to get the pressure field as well as the velocity field. Let us go for the same things, we will extend it to next level. So, let us go for the Navier-Stokes equations derivations. As I said it earlier, I am not going to for a step by step derivations which you can get it any fluid mechanics books. Okay. Basic my idea is that what are the assumptions we have and what we are considering it, and how we derive the Navier-Stokes equations with these assumptions for the viscous flow. So, we are now moving from the Euler equations to Navier-Stokes equations. Euler equation does not consider the viscous effect, whereas Navier-Stokes equations we want to consider the viscous effects. That means, in a fluid domains you consider a very tiny size of control volumes, which is infinitesimally small control volumes, in which you consider it not only the pressure and the velocity, the field variation, continuous functions, also we introduce a trace component. That is what, if you look at that, what we do it, that we consider the control volumes, and over this control volume surface we define the trace components. That is what we follow it, the shear stress component in z direction and the normal stress. On the surface, if you look at this x, y, z plane, so I have the plane surface, and in this plane surface the normal components I give it sigma x, means it is a plane the perpendicular to the x directions, that are normal stress what I am getting it here. Okay. Normal stress in the x directions over this plane, that is what it is, these planes having a dy and the dimensions is the dz. Dimensions is the dy dz in this plane which is a perpendicular to x, that the stress, the normal stress I define as sigma s. How do I define the shear stress components? Shear stress components I define it like tau xy. What does mean indicates here? Tau x indicates that it is a perpendicular on the surface which is the perpendicular to x plane. Okay, the perpendicular to the x plane. The first coordinates the perpendicular to the x plane. On that surface it is that. The second subscript indicates for us and which direction it acts it. In this case it acts in the y directions. So, this is a tau xy. It is acting on the surface which is a perpendicular, having a perpendicular to x axis, and that axis part what we are looking at, that which direction it is aware. It can work in a z because it is a perpendicular to x plane, that can work in a z direction or the y directions. If it is acting on the y direction, we define it as tau xy. If it is acting in the z directions, we define as tau xz. Please draw a control volumes and designated all these shear stress components. That is what is always difficult for a students, but please try to do it, that draw a small infinite small control volume dx, dy, dz, then sketch all these the normal stress and the shear stress components. Like here tau xy, this is tau xz. Same way, if you are coming to this plane, if you look at that, I am coming to this plane, okay, which is the perpendicular to the y directions. This plane perpendicular is in the y directions. If is that, I have a sigma y, I have a tau yx, because this component acting along the x directions, I have a tau yz. Same way I can notate it, the in each plane we can define it the stress components. That is what I encouraging as a students, you please draw the control volumes, infinitely small control volumes with a dx, dy, dz, and considering these notations, please sketch all these stress components acting on these all the surfaces. Please visualize that. That means you have considered a control volumes with having a 6 phases, and each phases we want to derive it, we have to define it what is the stress components acting it. Stress into the area is a force. So, that is what we are looking at, we have to derive as a trace components, and we are designating with a 9 trace components of sigma x, tau xy, tau xz, tau yx, rho y, tau yz, tau zx, tau zy, and sigma z. So, that is what is called trace tensors or trace matrix. So, any small infinitely small control volumes, if you consider dx, dy, and that what we can define as a trace components on the all these 6 facets, all the 6 surface facets, we can define this shear stress component. This is valid for the solid mechanics, this is valid for the fluid mechanics. So, any small solid object, if you take it, you can define as a stress field like this, okay. Stress tensor like this with having a components of the 9 components, we can define it. But some of the cases we can, if I take a moment about the axis through the center of the element, I can write this part, which indicates is that just I am equating the moment. If I going through the axis, which is the center of the elements, I can get it force into area distance and force into distance. If I equate this part, I am getting tau xy is equal to tau yx. Okay. The same concept I can use it for other facets to find out there is a tau yz zy. Tau yz is equal to tau zy, tau zx equal to xz. So, that means now instead of the 9 components of matrix of the shear stress, we can consider it's only the 6, because other 3s are equal to that. So, tau xy is equal to tau yx tau xz is equal to tau zx. So, only we have no unknowns of 6 trace components. That is what is a simplifications. That is what we do it for this infinitely small control volume. Now, if you understand this concept, then it is a very easy to derive these Navier-Stokes equations. So, because we have considered infinite small control volumes, over that we have defined the trace field. Okay. Now, we have to define it. The trace fields what we have defined in the 6 components, they also have a continuous functions within that. So, again we can follow the Taylor series approximations for different facets what could be the value if at the centroid we know it. So, that is the reasons what we do it. Like for example, if you look at these figures, that I am looking the sigma x variations at dx by 2 distance on the surface. If the sigma is at the centroid of these infinite small control volumes, that is what will be sigma s, the partial derivative of dx by dx by 2. That is the approximation of the Taylor series approximation. Exactly same way as we did it for u and v components, we are doing same approximations as a sigma s is a functions variability in the space and the time that can defined as what could be the value if I know the centroid value, what will be the value at the dx by 2 positive side or dx by 2 in the negative side. Just that means I can know it what are the force components are acting on these x directions. Okay. Some are the normal stress component as well as the shear stress components. These are normal stress versus into the area, it is a force because of normal stress. What is the force is acting it? This is the shear stress along this x directions, how it is acting it, and also the shear stress along this x direction because of the z field, how it is coming it, and then you have the force component because of gravity of these infinitely small control volumes. That was sigma s into rho into dV is a volume of this control volume is equal to dx dy dz. That is very simple things. That what is should be equal to the mass into accelerations. Mass into accelerations. Let me summarize what we have done it now. For the same small control volumes, we have trying to write or trying to apply the Newton's second laws for that control volumes, where the stress distributions we are considering, and from that stress distribution we are trying to find out what is the force acting along the x direction. That is what we are doing it. That is what will be the mass into accelerations in the x direction. That is what we have done it. Simple things, the same Newton's second laws of motions, nothing else, but we have applied for infinitely small control volumes with a stress distributions which are representing a force acting on this surface and also the gravity force as you know it. So, if you look at that, if I simplify these equations, I will get this part. Okay. So, that means again we are coming back to the equations which will have this local accelerations and convective acceleration terms. Then we have the terms in terms of sigma s tau yx tau zx along the x directions, along the x direction. Same way, looking these equations, you can write it what could be the equations for the y direction and the z direction. It is a simple thing. So, just look at these equations, you can write it. If I try to write the equation motions on along the y axis, I can instead of u, I can use the v, I can instead of gx, I will use gy, and similar way I corresponding stress components I can write it. Once I write the y axis things, I can write for z axis because all are the similar, only we have changing it the scalar velocity field and gx, gy, gz components and the stress components. So, that is the basic concept is just to apply Newton's second laws into these smaller control volumes where we have defined the trace variabilities. stress continuum, and that basis, on that basis we have derived these components. So, try to understand this and try to encouraging you to write the equations, so that you can feel that what is it's coming it. Now, if you look at that, still we have written the equations of motions in terms of accelerations components, in terms of the stress component. Okay. We have not written in terms of velocity gradients. So, reduce the number of dependent variables, we have to write the stress in terms of velocity gradient. As you know, we know from Newton's laws of viscosities that the shear stress is having a linear proportionality to the velocity gradient or the shear strain rate for Newtonian fluid. The fluid we obeys that laws. Okay. So, if you look at that part, that means again I can derive it, the stress components what I have in terms to the, in terms of velocity gradient, in terms of velocity gradient. That is what is Newton's laws of the viscosity. So, if you look at that part, that is what is saying that this normal and the shear stress components we can relate it to the velocity gradient. Viscous stress are proportional to the shear strain rate, which is there in Newton's laws of viscosities. If you look at that, now what is we have the problems. The problem is not a one dimensional problem. This is a three dimensional control volume we have considered it. It will have the two deformations. One is a linear deformations, another will be volumetric deformations. So, we need to consider the stress due to the linear deformations and the stress due to the volumetric deformation. That is what we consider the linear deformations by the dynamic viscosity, and the second viscosity we just introduce it. It is not a dynamic viscosity, it is another viscosity which consider it the stress formations because of volumetric deformations. Thus, any object when you have the stress field, it will go through linear deformations as well as volumetric deformations. If you consider that things, I am not going more details, the normal stress in the x, y and z directions can be written in terms of pressure, in terms of velocity gradient, in terms of volumetric deformations into the mu s. Mu s stand is a second viscosity. Please go through advanced fluid mechanics book to try to understand why do we have the two factors, why do we have a plus and minus, but try to have a visualization. Now, I can derive the normal stresses in the x directions is a functions of the p is the pressures, the velocity gradient representing the linear deformations, and I have the volumetric deformations. That is what I can write. Same way I can write for sigma s, sigma y and sigma z. So, normal stress components we have written it in terms of p, in terms of velocity gradient, we have a proportionality constants of mu s is the dynamic viscosity and mu is the second viscosity which takes care of volumetric deformations, the stress generations due to the volumetric deformations. If you considering that and go for the next level, looking that what could be happen to the shear stress component. That is what any fluid kinematic chapters, if you go through it, we can easily write it the shear stress component in terms of the velocity gradient with a mu stands for a dynamic viscosity. So, we can write it. Then the Stokes hypothesis says that the second viscosity effect is small, okay, that is not big because of volumetric deformations. So, we will not have a that much significant. We can approximate is minus 2 by mu by 3, that is we can approximate it, and similar way the pressure we can quantify it as the average normal stresses, and negative indicates it acts the opposite directions of the stress field. So, if you look at that way, you have a sigma y, sigma z, 1/3 of that, that means you are summing up and averaging it and you are computing what will be the p. Just to try to look at that if my infinitely smaller control volumes are dx by dy is tending to the 0, that is what will be the average normal stress is equal to the pressures, and the directions to take care of we have introduced the minus. Okay. So, now if you look at that, if I put it all these stress components into the basic linear equations of motions, I will get it same concept. Okay. That means I will get it local accelerations, convective acceleration, the pressure terms are going, Laplace terms are coming it here, plus I have a components because of volumetric deformations. That is just substituting all the values, and which, as I said it earlier, I am not going to do a step by step derivations. Please look at the step by step variations any of the books, but let us understand these equations, which is the Navier-Stokes equations. Okay, is Navier-Stokes equations for any fluid flow, we can solve it if you look at. But what is there in these equations? If you look at that, it is exactly whatever we have this. If I consider dynamic viscosity, the kinematic viscosity is 0 because of non-viscous flow systems, it comes out to be Euler equations, that is supposed to be. Okay. But that means in a Euler equations we have a accelerations component, we have the component of gravity force component, we have the force per unit for pressure unbalance, but we have introduced now the viscous effect. That is what you try to understand. This is what we have considered the viscous effect as the Laplace equations of u, and this part, it is a volumetric part. So, if you try to understand this is the part what we have introduced in the Navier-Stokes equations, additional components to the Euler equations. As we considering it, the fluid has a viscosities, and that frictional things if I consider as a linear deformations, as a volumetric deformations, we can make it this component additional components. Any of the computational fluid dynamics that they very detailed discuss about these equations, but I just want to summarize it. What we are trying to get it, we are again getting a nonlinear partial differential equations with a more nonlinear component like Laplace second order components are there, and we have these components are there. So, if you look at this way, the more complicated equations we are getting it as a nonlinear partial differential equations to solve the fluid flow problems considering the viscous effects, considering the viscous effect. And here also we have this 4 dependent variables. Who are there? They are velocity u, v, w, velocity scalar components, and the pressures. But we have the 4 equations, 3 linear momentum equations, 1 continuity equations. So, if you considering that, we can solve it, and today's it is possible to solve it. There are a lot of solvers are there for the Navier-Stokes equations commercially, or many sources are there nowadays. You can get a Navier-Stokes equation solvers. That is not a big issue to solve these equations, but it looks a very complicated equations in terms of nonlinear partial differential equations with 4 dependent variable u, v, w, and p, 4 independent variable, the space coordinates like x, y, z, and the time. So, how to solve these things? I am not going to tell much things now. Let us come back to the just solve these equations, taking example problems. That example problems which is we have considered from FM White books, just to demonstrate it that we can use these equations to get it some analytical solutions for a fluid flow problems. That let us consider incompressible, the flow is incompressible, density does not vary with time, velocity field is given, and if you look at this velocity field, you can interpret it many things, like the velocity field does not have the time components, it has only x and y, there is no z component, and the w part is equal to 0. So, this have to consider it before solving the problems, because when you try to get analytical solutions, you try to understand what type of velocity field is given to us, and the density field. Density says that is incompressible, that means density doesn't vary. Okay. So, if you considering that part, we have to determine under what conditions, that means we are looking the solutions of the Navier-Stokes momentum equations. Okay. If this is the velocity fields, what is the pressure fields we are looking at, or does this velocity field satisfy the Navier-Stokes equations? That is what we are looking at. So, what we do it, like we just try to apply this Navier-Stokes equations and substitutes all the terms here. Okay. All these terms, we just compute it, okay, in Navier-Stokes equations of the first x and y and z directions, substitutes all these things. Okay. This is what we do it, first partial derivative, second partial derivative with respect to x, respect to the y, then we substitute these values and we try to find out that what will be these three equations. If you look at these three equations, you can you can find out this equation is very simple, because we can integrate it. It does not have any component. So, we can integrate these integrations with this, we can get it. Next part. Okay. So, that if you integrate it, you can see this pressure is varying like this. Okay. But there is a constant which is maybe a function of x and y, we do not know it. Second point is coming, okay, we have integrated one equations to got it, what could be probable solutions of this with a unknown functions f1x. Is it correct one? So, what do we do it? Again we use these equations to check it, other two equations, do they satisfy? That is what we did it. The differentiated with equations y with respect to y, respect to x, then you just compare it and we found it, these are also the same values. That means this velocity field what is given it, that what it satisfies the Navier-Stokes equations. Now we are looking at what could be the pressure field. Again these are all, I can say that it is just a differences and integrations to just find out that what will be the integration constant values. That is the reasons again we substitute equation 4 into equation 1, 2 into the 1 and obtain what will be the f1x. So, once you know this f1x, then we integrate it and do the differentiations, still we get it the value f2 value. Now, we will substitute it, which is gives us the pressure field. This part we got it, this is the part we got it after integration differentiation of these previous equations, and that is what is giving us the pressure field which satisfy the velocity field, pressure field for this the flow domains where the Navier-Stokes equations is hold good. Before completing these things, I just want to show you that similar way we have applied the Navier-Stokes equations for the fluid flow problems in a channels. We know it, many of the times we put a small obstructions like a Prokopine structures, the river training works, and try to know it, does it work it, how much it is working in terms of velocity reductions. That is what we try to do with a 3-dimensional models. Okay, so this is 3-dimensional models which has the Navier-Stokes equations with the depth integrated. Okay. The turbulent flow which will commit later on will have a eddy viscosity, K-epsilon model and the depth integrated logarithm laws and all, and it is a solver of the finite element approach, and that solutions what it gives is just going to give you confidence that we have put the structures here, we try to measure the velocity, is a numerical models, try to find out that, and if you look at these velocity distributions, and this is what the velocity distribution measure from Flume experiments. You can see that there is a velocity reductions because of these obstructions. That is what is clearly visible from upstream the velocity distributions and the downstream velocity distributions. There are significant velocity reductions are happening it in experimental data as well as the numerical modeling of Navier-Stokes equations. So, it is now it is a possible, there are the models are available which solves the Navier-Stokes equations with some approximations like depth integrated concept with turbulent structures. We can get it the solutions like what we have done it for a river training work with having the Prokopine structures, small obstructions, we can see that how much velocity reductions are happening. Same things you can look at how much velocity reductions happening at the experimental levels. So, those things we can conduct it, and it is possible nowadays we can do it as we consider as a Navier-Stokes equation solvers. Let us come back to derive the momentum equations for river flow, unsteady gradually varied flow. Okay. The variations in the gradually as well as the unsteady flow. If you look at a river as we are considered here, it is a river, this is the bed, this is the free surface, and there will be the energy gradient line. This is a hydraulic gradient line. And if I consider these channels having a making angle theta, is making angle theta, the channel is making or the river is making angle theta, and this is the free surface, this is the energy gradient line. The slope of energy gradient line we define as SF, and we also define its the slope of bed is S naught, which is equal to tan theta. Okay. But the geometry of this cross section geometry of the rivers can have a complex like this, okay, as we are looking for area integrated concept. It can have a like this, the free surface can be here, and ZC is the centroid point where the pressures acts it. So, in this field P is having the variations, the pressures acting on this field is having the variations, also the A also varies it. So, P into A also have the variabilities. Pressure into area is the force. Force also we are considering is a variability from along the x directions. Along the x direction, the force into area is very exit. If this is my control volume, this is my control volumes, I can easily interpret it what are the forces acting on this control surface. One is the force components, hydrostatic or hydrodynamic part. Here is hydrodynamic force components are there acting on these two surfaces. The force acting on the free surface we can negligible it, but there will be a force, the frictional force acting on this. The frictional force acting on the bed surface we can quantify as a tau naught P dx. If you look at this, tau naught stands for the bed shear stress, the shear force acting on the bed times of the perimeter of the flow, weighted perimeter of the flow, and to the DAS coordinates. That is what the frictional force acting on this. Frictional force we have designated as a bed shear stress acting on this bed, that is what we are defining it. Then we are defining the gravity force components. As it is a inclined phase, you can find out it has a component in x directions along these directions, along the x direction as a gravity component of FW sin theta and FW cos theta component. So, that the resolutions we have done it, that is what is the bed frictional stress resistance is tau times of fluid data, weight of the fluid in this control volume. So, we have considered it and theta is included. Now, again we have to apply the same Newton's second laws. Okay. Find out the net force difference in the x directions, that is a PA, and the force acting on this part, then the force component due to the gravity, frictional force is equal to mass into accelerations. If you look at that, is the same concept we are assuming it, only you have changed the control volume, we have changed the force components, we have a different assumptions for that. Like in a free surface there is no force components, we have considered this hydrodynamic process is a PA which is a variabilities we have considered it, and we find out the frictional resistance force and all. That is what is sum of the forces we did it is equal to mass into accelerations. That is the component, and the accelerations we can define as only this one directions area average u value. That is what we can define as local velocity and the convective velocity in the x direction. So, we have a one dimensional equations, in x directions. That is try to conceptualize that we have considered the river and we are just looking at the longitudinal directions, what is happening. We are not considering much lateral directions, what is happening, or the depth variations, what is. We are just looking at along the longitudinal directions, how these force components are there. That is the area average velocity we have. We are looking at the local accelerations, we are looking at the convective acceleration terms. Now, we have to simplify these things. Here equations components. So, if you look at this part, we can get these components as well as we will get it the components, the gravity force components, and we have the bed shear force components, then we have accelerations components what we have. Just rearranging these equations, divide the weight of the fluid, I will get this the equations on this part. So, in these equations if you look at that is quite interesting to know it what is this value, that is why it is quite interesting for us. Otherwise, we know the S naught is a bed slope, SF is a friction slope, we have a local accelerations component, we have a convective accelerations components, and we can define its a bed shear stress in terms of friction slopes. That is any of the open channel book you can find out with a small contour volumes we can get it the relationship between the bed shear stress and the friction slope. If I try to find out what is these values with a approximations of hydrostatic pressure distributions, with approximation of hydrostatic distribution, this component I will get it finally say is equal to del H by del X. So, that is why it is a quite interesting approximations where you have done it. In this case, we have considered is a hydrostatic pressure distributions. Since is a hydrostatic pressure distributions, we can compute the what could be the pressures at the centroid of this area, and that what if you simplified it, finally we are getting it this component is nothing else the gradient of the flow depth. H stands for here the flow rate, gradient of the flow depth. That is what will give it as the this component. This is the bed slope component, friction slope component, local accelerations and convective accelerations component. Now, if I substitute all the things, I am getting these equations which is known as Sand-Vinet equations. Is known as the Sand-Vinet equations, and this is you know about the Manning's equations. More detail about the Sand-Vinet equations we are going to discuss in the next class. Just to conclude this part, I want to say you that we definitely do a lot of things to try to understand the rivers, but try to understand this quote that a good river is nature's life work in song. So, just try to understand what do we mean by the rivers. We try to frame the rivers in mathematical forms, but still our knowledge is limited for the natural rivers. With this, let I conclude this lecture.